In this section, we're going to talk about galvanic electrochemical cells, so also called voltaic cells. Those are the same thing. We'll talk about the different parts of them and the chemical reactions that occur. So in the last video, we said that electrochemistry means the interconversion of chemical energy and electrical energy. So we're focusing on redox reactions, and that all sorts of things that you see in normal life are examples of electrochemistry. Now, in the lab, an electrochemical cell might look something like this. So we imagine two compartments that are connected by a salt bridge, and that we have our two half reactions happening in these two different compartments. And so even though a battery doesn't really look like this because of the way that we package it, we can imagine that the same things are happening. So the electrochemical cells we're going to talk about right now are called voltaic or galvanic cells. These cells react spontaneously, where the chemical energy is spontaneously converted into electrical energy. And we can describe that electrical energy as electrical current, which is electrons moving through a wire. The opposite, an electrochemical cell that goes non-spontaneously, is called an electrolytic cell, and we'll talk more about those later. A couple of conventions for us to talk about. We need to define the words anode and cathode. And so again, thinking about a battery as being an electrochemical cell, it has two terminals. One of those is the anode, which is where oxidation happens, where we give it the negative sign because electrons are produced there. So from the perspective of the thing you're plugging in, the wire connecting the two electrodes, the anode is where electrons come from. And so remember that oxidation is loss of electrons. Electrons are produced there, and they travel through the wire to go over to the other side where reduction happens, where electrons are consumed. Because the electrons are leaving the anode, that also means that anions are going to migrate toward the anode in order to replace that negative charge that's leaving. The same with the cathode. So the cathode is where reduction occurs, where electrons are consumed because the electrons are being gained by the reaction. It's where cations migrate toward in order to replace those consumed charges. And so we give it the positive sign. One way that I remember which side is the cathode is I think about a red cat, red like reduction, cat like cathode, and that works for me. So you can think about a red cat or not, your choice. All right, so here's an example of a galvanic cell, a picture of one. Let's look at it together. So in this cell, our first task is to label the cathode and the anode. And so we said that the anode is where electrons are produced, and because the anode is losing electrons. So if we look at our flow of charges here, we see that electrons are coming away from the copper electrode and they're going toward the silver electrode. So that means that the copper electrode is the anode and the silver electrode is the cathode. Okay, we can write the half reaction for each compartment. So in the anode, we know that oxidation is happening. So we're going to go from the lower oxidation number to the higher oxidation number, and therefore produce electrons. In the cathode, we know reduction is happening. So we're going to go from the higher oxidation number to the lower oxidation number and consume electrons. We can write this as an overall balanced chemical equation by thinking about balancing the electrons. So to balance the electrons, we're going to need 2 of the silver reactions. And so we can imagine 2 silver plus ions plus copper become copper ions plus silver. Okay, so what's happening is that, in this reaction, is that the atoms of copper in the copper electrode, so in this like copper metal piece here, they are leaving the copper surface to become part of the copper solution. And in the same way, the metal ions, the silver ions in solution, are becoming part of the metal surface when the ions meet up with the electrons to make silver. Okay, and so we can explain the role of potassium and nitrate in here. And so potassium and nitrate, and we also have some sulfate. So those ions are called electrolyte. And the job of the electrolyte is to help keep the charges balanced, so that way, as the copper ions are leaving the copper metal surface, that's going to make that side more, so build up positive charges there. So the nitrate ions will migrate through the salt bridge toward the anode side. Remember we said anions migrate toward the anode in order to balance those charges. In the same way, on the cathode side, we'll see potassium ions in the salt bridge migrate toward the cathode, because as the silver plus ions become silver atoms, then we decrease the positives in the chart in that compartment. So the role of the potassium ions is just to keep up with the charges and make sure that everything is neutral. We can express this in electrochemical shorthand notation. In electrochemical shorthand notation, we always start with the anode half cell. So we're going to write, we do the anode first, and we're going to start with the electrode and then move, so with the electrode because it is the reactant, and then we're going to draw a line, and that's going to become copper 2 plus aqueous. So that line represents that there's a phase transition, that we have solid becoming aqueous solution. So that's what happens in the anode compartment. We draw a double line to represent the salt bridge, and then we can show the reaction that happens from reactants to products in the cathode compartment. So that means we have silver plus ions, and then phase boundary, silver atoms. Okay, so here is our electrochemical cell and all the pieces of it. That electrochemical shorthand notation, just to sort of go through that again, we always write the anode half cell on the left, even though it was on the right in our picture. The anode happens on the left, and we write the reactants and then the products, so showing the oxidation left to right, so that, as you can see from this arrow, that electrons flow in this direction. Then we represent the salt bridge with two vertical double lines, so a vertical double line, there we go. And then the cathode half cell is on the right, where we show the ions, vertical line for phase boundary, and then the solid. And so this helps us to see, instead of having to sort through what's a reactant and what's a product, it shows us here's what's happening, reactants, products in the anode, here's what's happening in the cathode, reactants, products. Okay, so some special things to think about when you find yourself looking at electrodes. Inert electrodes are used when no other solid is available. So in the example we found, we had a solid reactant and a product. So we had silver solid and we had copper solid. If our reactants and products are all aqueous, we can use an inert electrode in order to help the electrons meet the molecules. Platinum is the most common choice. So if you see platinum, that is an inert electrode. It's not part of the reaction. How do we choose the ions in a salt bridge? The point is that they should not be redox active, and they shouldn't have a lot of acid-base characteristics. So common redox electrolytes are things like potassium or sodium or lithium ions, because they don't have very much redox chemistry, and the conjugate bases of strong acids, so things like nitrate or perchlorate, or you can use chloride, but the halides tend to have some redox chemistry, so those are less common. So you notice that these are the conjugates of strong acids and bases. They are commonly redox electrolytes. How do we know when an element is part of the reaction or if it's just inert? Well, if you write your balanced redox reactions and you don't use those ions, then they're inert. Okay, so let's go the other way. Can we draw a cell based on a shorthand? Okay, so we said that the anode is always on the left side. And so that means that our electrode is going to be made out of aluminum, and that is going to be producing aluminum ions in solution. Okay, so there's our cathode compartment. In our anode compartment, we have permanganate becoming manganese 2+, and that's going to be in the presence of acid, so there's going to be some H+ in that solution. We see that we have here an inert electrode, so this electrode is made of platinum. And what happens is that the permanganate sort of rests on the platinum in order to receive electrons and produce the manganese 2+. We also know that we're going to have some inert electrolyte ions. So we might have potassium and also nitrate. That's my favorite electrochemistry electrolyte. And so the cations will migrate toward the cathode and the anions to the anode. So that means that there will also be some cations and some anions in each compartment. Okay, they're in the salt bridge. Now, let's show the direction of electron flow. We said that the aluminum atoms are becoming aluminum ions, so that's going to mean that electrons are produced at the anode. So here's our anode, and they're going to travel through the wire to light up the light bulb, and then they're going to be used to reduce permanganate to manganese 2+ at the cathode. We said in a galvanic cell that the cathode is the positive electrode and the anode is the negative electrode. Okay, so we have our two compartments, anode, cathode. We have our salt bridge. And we've represented what this shorthand would show us, remembering that this is the anode reaction, and here's the cathode reaction. Okay, so check yourself. Which of these statements is correct? Electrons leave the cathode and travel toward the anode. Nope, we said it's actually the opposite. So this one, not correct. In a galvanic cell, the cathode is negative. Nope, we said the cathode is positive, remember? Reduction occurs at the cathode. Red cat, yes, this one is true. Cations migrate toward the anode. Nope, cations migrate toward the cathode. Electrons are produced at the cathode. Nope, they're produced at the anode because they leave the anode and travel toward the cathode. All right. So this has been a brief introduction to electrochemical cells. I encourage you to do lots of practice working through the parts and ask me questions or go to tutoring or ask questions in office hours, and you'll get the hang of this soon.